Okay, so here's where we were last time. We just kind of barely started with this page. The idea is that you remember this are some ideas I threw at y'all when we were talking about the fundamental theorem of line integrals. And you can write it like this and interpret that dot product as being change density because it's change per unit length, or you can write it like this and interpret this, the gradient itself, as being an oriented density. I mean, it's an abuse, right? It's a stretch. Kind of have to get into a loosey-goosey kind of a mood to buy it, but you can view dx as being an oriented size, and thus this is, I guess you could call it an oriented density. And it was very natural in the sense that if you look at the resulting, the direction and magnitude, well, let's see here, the magnitude is telling you how steep it is, right? And of course, if you're talking about a change density, how steep, how fast is the change happening, right? That's, in some sense, naturally the magnitude of the change density. And then the direction that it points is, well, it's pointing uphill. It's pointing in the direction of fastest increase. It's pointing in the direction that change is happening, right? So pretty natural breakdown. The idea of an oriented density is a recognition that the way things change has both a direction and a magnitude aspect to it. And the oriented density literally tells you both of those aspects. So we're going to make the same argument down here. And recall that when we first wrote down Stokes' theorem, we wrote it down like this. And as such, you can interpret this dot product as being circulation density. And of course, that was one of our big takes. And very important, and I'm a big fan, etc. But if you rewrite the theorem like this, then again, you find yourself able to make an interpretation of curl itself. And again, this idea of an oriented density. Because, well, again, after all, and again, think flexibly, right? ds, kind of an oriented size, you might call it. Its magnitude is the size. Its magnitude is literally the area of a little piece of your surface. And the direction is the orientation. So along those same lines, curl. Oriented density. And again, it's just kind of a perfect breakdown in terms of direction and magnitude. The magnitude of the curl is going to tell you, in some sense, how fast is this fluid rotating? Are we talking about a really fast rotation? Or are we talking about a gentle, kind of slow rotation? Right? And then the direction that the curl points is telling you what I'm going to loosely call here for just a quick moment the direction of the rotation. And if you want to talk about how something is rotating, you would talk about the axis that it is rotating around, right? Whenever you have a rotation, that rotation is always around an axis. So that's what the direction of the curl tells you. So just to put all this together onto a picture, the curl is a vector. The direction that vector points tells you the axis of the rotation, just like we had here, right? And the magnitude of that curl is going to tell you in some sense how much of a rotation is there. And let's not worry about units or anything precise and specific. It depends on the nature of the fluid and various constants involved and assumptions you make. That's not our problem. That's context by context. But longer curl means, in some sense, more rotation. All right. So I think this is a really important idea. Now you hopefully get a sense of why I felt it necessary to make this seemingly forced, seemingly clunky, weird take on how to interpret the gradient vector is because it sets up a point of view on curl, right, that helps us understand what curl looks like geometrically, physically, right, which we didn't have any really good alternatives of, right? Now, we knew what gradient was, We didn't really need this point of view for gradient, but we really needed it for curl. Okay, so now just a quick, what's the word here? Just a couple of example kind of cases, just to show that this tracks, that this is kind of a reasonable take on what curl does, and in particular that curl.in is what computes little bits of circulation. I've got a vector field drawn here, this vector field F. And you can see that vector field has kind of a rotation to it, right? There's a little bit of a tornado kind of aspect to that fluid flow. And so there is a curl that's about like this, right? And I'm going to consider this same vector field now, this same flow, in two different scenarios. So up here, one scenario, one little piece of surface. Same vector field down here, different surface. Let's just see kind of how this plays out. So, okay, starting with the top example, notice that the way this is set up, the way the fluid is rotating, you might say, tracks pretty nicely with, I'm going to abuse the term here, the way the boundary is rotating, or it will be a little bit more clear. If you're moving around the boundary, then you yourself are kind of rotating because that boundary is kind of round. So keeping in mind that circulation is the extent to which the fluid is flowing along the curve, I say we've got a pretty good example of that happening here. This fluid really is flowing around with that boundary curve. And so you would expect to find a significant circulation of that fluid around that boundary. All right. Now, how does the curl vector pick up on that? Well, the curl vector is like that. The normal vector of my surface, whose boundary we were just looking at, the normal vector is like that. And notice the curl and the normal vector, likewise, pointing in the same direction. And so when you compute curl dot in, you're going to get a significant dot product, right? So the fact that these two are pointing in the same direction geometrically tracks very nicely with the fact that these two harder to sort of put your finger on things, namely the fluid flow and the boundary, are sort of also in the same direction. Okay. So reasonable, I hope, then, that this purple measurement is at least kind of in the same direction, kind of consistent with this blue calculation. Okay, now by contrast, let's consider this second scenario. In this second scenario, the fluid's still doing the same thing, same fluid, but look at our boundary curve. Our boundary curve it's just going in a totally different direction. Let's see if I can do this. The fluid, the fluid is doing kind of like this, right? And the curve is doing kind of like this. That's harder than it looks. This kind of a rotation, the boundary is doing sort of this kind of a thing, right? And then I think that's confusing. The fluid is doing this kind of a thing. They're just in different directions. There's not much flow of fluid in the direction that the boundary is actually going. Not expecting to get a lot of circulation there, right? So I'm going to say, yeah, not a lot of circulation. And just as it should, perfectly consistent with that, note the curl is that way, but my normal vector is that way. And so again, this dot product, curl.n, our measure of circulation density, our attempt to use vectors to get our hands on this little bits of circulation, this dot product is going to be small for geometrically sort of tied in reasons that are consistent with the fluid not really actually circulating. So anyway, this is just a plausibility argument that that curl does what I was claiming, that curl.n is doing what I'm claiming, namely it's measuring circulation density. Okay, so whatever that's worth. All right, moving along. Let's do some physical examples. The first thing that I have here, this is a rip-off of stuff we talked about a while ago concerning Green's theorem. So the premise here is that we have some sort of a two-dimensional fluid. I like to think of the surface of a river, right? And the water is kind of flowing along, and there might be rocks in there, and the water has to kind of flow around. But it's not just straight lines necessarily, but there's some flow on the surface of the river. And then we have a leaf floating in there. And the question is, how do you figure out the leaf's velocity? Well, the leaf is going to do exactly what the water does, right? If the water is going that way, then the leaf is going that way as well. Leaves don't swim upstream, right? The leaf is following the water exactly. Well, the water is doing what the vector field says. So the vector field itself is the thing that tells you how the leaf is moving. And y'all may recall there was a homework exercise where this was kind of the point to half of that homework exercise. Okay, but what about rotation, right? What helps us understand how the leaf is going to rotate? Well, the leaf is going to rotate the same way the water does, and the water's rotation is controlled by Green's, or is described by Green's operator. Right, so Green's operator is telling you how the water is rotating, and thus is telling you how the leaf is rotating. Okay, all review, all old news. Now, what's the three-dimensional version of this? So in 3 dimensions. Now, we can't talk about, the surface of a river. We need to be in space. So I changed the metaphor just a little bit. And now let's imagine, I like to imagine perfectly weighted balloons, right? That you don't want too much helium. They go up to the ceiling. You don't want too little helium, they drop on the floor. You want them just, 3 days after the party. You know what I mean? They're just at that perfect weight, and they just kind of float around the room, perfectly buoyant. Okay, what do the balloons do? They do exactly what the air tells them to do, right? If the air starts going that way, the balloons start going that way. Okay. So, likewise, how do they rotate? Well, the rotation of the balloon is consistent with the rotation of the air. If the air is kind of doing like this, well, the balloon's going to sit there and do the same thing. It's being pushed along by the air. Right? And how is the air rotating? Well, the curl vector is what tells you that. The curl vector tells you what's the axis that it's rotating around, and how fast, in some sense, and again, the units in particulars all depend on the specifics of the question, but whether there's a lot of rotation or just a little bit. Okay. All righty. Now here's a more technical example. This is magnetic fields. So y'all probably have some previous exposure to magnetic fields. If you don't worry about it. This is not a physics class, right? So I'm only going to talk about this to the extent that it's helpful to math, right? Physicists like to think that math is a tool for understanding physics. I tend to like it the other way around. I like how physics can serve as an example, as a manifestation, and thus help you understanding math ideas. Right? So I think this is a nice example of that. So here's how current works. Now, y'all probably previously familiar with current in a wire. Maybe you are, maybe you aren't. But so if you have a wire in a circuit, and charged particles just move down the wire. So current says, picking a point on that wire, as the charged particles are flowing through that wire, how many charged particles per unit time are flowing past your reference point? So it's a flow rate. Okay. All right, now in reality, not all charged particles are necessarily flowing through wires. You can have charged particles just flowing in space. Just like the air in this room, right? There's a flow of the air in here. You can have a analogous flow of charged particles. And this is called a current field. We usually represent the current field not by just the velocity itself, but by charge density times velocity. Y'all remember we had these two different points of view on how to use a vector field to represent a fluid flow. Okay, so current is a vector field, a flow field. And now here's a fact of the physical universe. I don't know why this is. I don't think anyone really knows why this is. This is just empirically observed. Apparently this is how our universe works. It is what it is. When you have a current, that creates a magnetic field. And as I have my flow field drawn there, the resulting magnetic field is something kind of like this. They tend to go kind of around, in some sense, around the current field that created them. Nobody knows why. Okay, so that said, we can consider then a scenario. Let's think about a closed curve here. And let's think about, likewise, if I can find the color, there it is. Let's think about a surface whose boundary is that curve. Just try to get that all the way filled in. Good enough. We have a surface, we have a curve, and here's a couple of things that you could think about in relation to that surface and in relation to that curve. One is, look, we got a surface, we have a flow of particles, right? Flow of charged particles that are moving through that surface. And reminder, when you have a fluid flowing through a surface, you can ask what the flow rate is. Stuff per unit time passing through your surface, right? So quantity per unit time. What's the total charge per unit time passing through that surface? And now let's think about that little phrasing that I just made. Charge per unit time passing through. That's current, right? If you imagine current in a wire, it's charge per unit time passing through some reference point on your wire. Same deal here, charge per unit time. So on that surface, you could reasonably ask, what's the flow rate? Namely, what's the current of our current field through that surface? Now, that's just one thing you could ask. Now, here's a different question you could ask. Recall that this current does create a magnetic field. The magnetic field, again, is going to be kind of, something kind of vaguely around, kind of like that, let's say. There is a magnetic field, and it seems to be going kind of around that boundary curve, right? And so you could reasonably ask, how much circulation is there? So on this curve, you could ask, what is the circulation of the magnetic field around that boundary curve? Well, it's just a question, something you could ask, something you could measure. Right? So here's the weird fact of it all, and that is that if you measure these things, you can just do in a lab, you can measure how much current there is through a surface. You can measure what the magnetic field is, and in particular the circulation around some curve. And it turns out that these are closely related to each other. This is just empirical. Again, don't try to think about why. This is just observed, right? Likewise, don't try to think about why gravity points down. It just is. That's the nature of the world we live in. And likewise, these are proportional. That's just the nature of the world we live in. Okay. All right. How are we doing so far? All right. Okay. All right. Well. flow rate is a flux. And think back to the very first time that we wrote down flux. The very definition of flux, our starting concept of flux, was flow rate of fluid per unit time through your surface. And that gave us our flux integral, our vector surface integral that I have written down here. Aside from this constant that's on both sides, that's on both sides, so whatever, it's just there. So that top line, again, is an old idea. The bottom line down here is just straight up Stokes' theorem. Circulation is flux of curl. You write that down as well, and you're going to notice, well, you've probably already long since noticed that we have one of these same little sort of rectangular little equation array kind of things like we had when we were talking about gravity, and we were talking about electric fields and stuff like that, right? So I deliberately set this up. I'm a big believer in analogies. I wanted y'all to see how the argument here really tracks with what we've made in those previous two cases. And having reason to believe this, Stokes' theorem then would have us also believe this. Right? And so these two equations are very often viewed as different equations because, well, gosh, one's about current and circulation, the other's about a flow field and a curl. They seem pretty different, but they're actually intimately related to each other. The Stokes' theorem makes them morally equivalent statements. For example, circulation density. Right? So very, very closely connected statements. Thank you, Stokes' theorem. And in fact, these are both considered Maxwell's fourth equation, at least by the way I like to number them. So typically considered the same equation, just kind of two different versions of morally the same statement. Okay, and of course, though, to be able to make that conclusion, to be able to see how these really are kind of morally the same statements, Stokes' theorem is just essential for being able to draw that conclusion. So nice application of Stokes' theorem. Okay, moving along. This is all old news. Let me do this quickly because we've already done it. We have three different statements involving path independence and gradient. These are all basically saying the same thing. Again, regularity issues aside on our problem. And reminder, we also had these two statements, and these two statements are pretty easy to relate to each other. After all, if there's a function, all of whose double integrals are 0, come on, how's that possible? The function itself has to be 0. Okay. So we made a connection between these two groups of statements by using Green's theorem. Green's theorem, after all, says that this circulation is always equal to this double integral of Green's operator, and so therefore these things connect, and therefore we have our local test. And if you want to know, hey, I got a vector field, is it a gradient? Should I bother finding an anti-gradient? I don't want to exert a bunch of effort trying to find an anti-gradient if there isn't one. Right? Is my vector field path independent? I would love to be able to use path independence in my argument, but I better not unless I know it is. How do I know if a vector field's path independent? The answer is you compute Green's operator. You see if you get 0. If it is, you're in business. Right? So really nice test, really nice argument. And again, the thing that makes it all work is Green's theorem. Okay, now that was a quick review. At the same time that we did this some days back, you may recall I also stated this, and then I made a vague reference to, we'll eventually have a more powerful theorem that applies in 3 dimensions that allows us to actually see why this works. And at the time, we had not yet covered Stokes' theorem, so we weren't at that time able to make the argument that we're about to make now. But it's as easy as you think in the sense that these we've already related to each other. Old news. These, I need a different color. These, well, they're different statements, but again, pretty easily related. What vector field, in this case it's going to be called curl F, but what could this integrand here be since that all of the fluxes are 0? All of them, for every surface. Only the 0 vector field could do that. Okay, so now we have exactly what we need. Stokes' theorem literally tells us exactly this. It tells us literally that closed vector line integrals, namely circulations, are computed with a flux of the curl. And therefore, whenever this is 0, that means that's 0, and therefore we have connected all 5 of these equations, and therefore we've now demonstrated our local test. If you have a vector field, if you want to know if it's a gradient, you want to know if it's path independent, compute curl, see if you get 0. If it is, you're in business. Is that cool? All right, so that, like I say, fills in a blank that we talked about. Now we know why in 3 dimensions curl is our test. Okay. All righty. Okay, new idea. Another strong analogy. So y'all remember path independence, right? Let me remind you what path independence says. The idea of path independence is if you pick a starting point and fix it, and if you pick an ending point and fix it, right? So we're going to consider curves that start in that point and they end at that point. Start and end being what you might call the boundary of a curve. We're going to consider only curves that have those points as their boundary. There are some special vector fields, weirdly special vector fields called path-independent vector fields that say in those cases you get the same value of the line integral, whatever curve you pick. And that's a remarkable property for a vector field to have. Most vector fields don't have this property. I cannot emphasize that enough. I'm saying some vector fields, special vector fields called path-independent, have this feature. You'll always get the same answer, no matter what curve you pick, as long as you have the same boundary. Okay, and then recall as well we had this other formulation, and that is path independence could be viewed as all closed line integrals are 0. And of course, if you have 2 curves that start and end at the same point, then you can kind of put them together to make a closed curve. And we argued previously that this condition in blue is equivalent to this condition in orange, namely closed line integrals all 0. Okay, so that's a quick review of path independence. Here's the amazing next statement. You can take everything that we've written here, just shift the dimension by 1, everything still works. It's remarkable. So here we go. Let's do it. Surface independence, we call it. So fix a boundary. We're not going to be talking about curves, one-dimensional curves with 0-dimensional boundary points. No, we're going to talk about 2-dimensional surfaces with 1-dimensional boundary curves. So when I say we have to fix the boundary, that means that we're going to have a boundary like this, right? A boundary curve like that. Whatever surfaces we entertained, they have to have this exact curve as their boundary. That said, then, once you have your boundary fixed, there are special vector fields, believe it or not, where pick any surface you like, it doesn't matter. You'll always get the same value of flux, namely vector surfacing. That's remarkable, very surprising. Just real quick before we finish that off, note that is dimensionally analogous. Instead of talking about line integrals over one-dimensional curves, we're talking about surface integrals over two-dimensional surfaces. But structurally, same idea. Pick a boundary, settle the boundary, then pick any curve you like. Down here, pick any surface you like. You get the same value for the line integral up here. You get the same value for the surface integral down here. So really, really analogous idea, and likewise can also be reformulated in terms of the surface that you get by looking at the one and combining with the other in sort of an analogous way. Alternative formulation of surface independence is that closed fluxes, boundary fluxes, are all zero. Okay, so it's a really cool fact, and I'm going to give you all a different point of view on this next time when we have some more time to go through this. But I think there's a lot of ISMAC, right, to be had by looking at this picture. I've deliberately done the color coding, right, as analogously as possible, and notice how they're really the same idea. I mean, again, structurally, same idea. It's just that everything down here when you're talking about surface independence is just one dimension higher. And then, everything else adapted appropriately. Okay, before I go on, I want to recognize that most multivariable calculus books, ours included, as I recall, do not talk about surface independence. I think that's an outrage. Absolute outrage. It turns out this property called surface independence, really powerful computational tool. There are lots of, my old, college days, I made massive use of this idea of surface independence to compute stuff. And so it's a really important trick to know, even if only from a computational point of view. Right? And I'm going to show you an example in a couple of minutes. So really important to see how surface independence works. And again, it just kind of blows my mind that most multivariable calculus books don't even mention it, don't even acknowledge the existence of it. It's very weird. Anyway, for the record, even though it is not in our book, it is in our course, right? So you remember the content syllabus, talking about all the sections that we cover and with all the homework exercises on it. Don't forget there's a column called included material and another one called excluded material. The excluded material is stuff you don't have to worry about. Tear those pages out of the book if you're so inclined. Not that I'm encouraging that, right? But the included material is stuff you are responsible for, and surface independence is in that included material column. Okay. All right. So when we were talking about path independence, one of the first questions we asked was, is that even a thing? Are there any actual examples of path-independent vector fields? And it turns out, gradients. Every gradient, regularity issues aside, every gradient is path-independent. There is an equivalently good news answer here, and that is every curl is surface independent. So here we go. I'll try to explain what's going on here. We're going to entertain curls. We're going to look at fluxes of these curls. Right? So this vector field F, you see is a curl. Right? It's going to be a curl of something called G, whatever. Being as it is a curl, I claim that makes the vector field surface independent. I claim that makes this integral have to equal to this integral as long as S1 and S2 have the same boundary. Now, how would we see that? The way we see it is by using Stokes' theorem. So Stokes' theorem, starting with this first surface, I apply Stokes' theorem to this first integral. Here's what Stokes' theorem says. Stokes' theorem says that if you have a flux of a curl, right? Don't forget, F is a curl. The flux of a curl is this line integral. It's the line integral of the vector field whose curl you're talking about, around that boundary. Okay, so again, that's just applying Stokes' theorem. That doesn't prove anything yet, but we've applied Stokes' theorem to that left integral. Now let's apply Stokes' theorem to this right integral, again with the Stokes' theorem. And again, our vector field is a curl. We're looking at a flux of a curl. Again, we get a line integral, a boundary line integral of the vector field whose curl we were looking at. Now, all I've done with the green and the blue there is just apply Stokes' theorem to these two different surfaces, S1 and S2. Of course, the whole idea here is that S1 and S2 have the same boundary. If they have the same boundary, you're computing this circulation around the same boundary for each one of these, and that means that you're going to get the same answer. And therefore, these two fluxes are equal. And therefore, this vector field is indeed surface independent. Really nice little argument there. By the way, I have a suggestion, something y'all can think about spending a couple of minutes looking at. You know, I'm a big believer in the compare and contrast. You know, when things are somewhat analogous, you want to look and see in what ways are they the same and in what ways are they different. Look back at how we used previously the fundamental theorem of line integrals to show that gradients were path independent. And that's in the lecture notes. It's right there in the notes. It's back at, oh gosh, what section is that? Well, y'all can look that up, right? But we use the fundamental theorem of line integrals to show that gradients are path independent. Here, we're using Stokes' theorem to show that curls are surface independent. And the arguments are extremely analogous and well worth looking to compare and contrast and notice how, wow, they really are very much the same argument. That's a suggestion. You don't have to, but I think there's a lot of good to be gained from that. Okay. Moving along. Also true, we're not going to prove, but not only is every curl surface independent, but also every surface independent field is also a curl. So this, and again, regularity issues aside, this is harder to prove. Don't try to prove this second statement, but still true. Good to know that, again, regularity issues aside, surface independent is just the curl. All right. Now, I'm sure you all recognize this structure. We've seen this structure twice today. We saw a review of how something that looks vaguely like this allowed us to find a local test for path independence in 2 dimensions. And then we used Stokes' theorem with an argument that looks vaguely like this to show that Stokes' theorem shows that in 3 dimensions, curl is our local test for being a gradient. Okay, so what we have here now is a different thing. Here we're going to be interested in surface independence. And remember, surface independence, we just established, all curls are surface independent, and I claim vice versa. And again, harder to prove, but it's true. And again, alternative phrasing of surface independence, closed fluxes being 0. So again, all that's discussed above. And then I'm just going to write down this little pair of equations, and the argument I'm going to make here for this green pair of equations is the same exact argument that we've made in previous circumstances, that you got some function, in this case called divergence, but this thing here, this integrand, all the triple integrals are always 0, no matter what solid domain you pick. How is that possible? All the triple integrals are 0 for every domain. The only way is if that integrand is itself 0. Again, I think a pretty believable argument. Okay, so how are we going to relate? How are we going to make a local test? How are we going to connect these dots? How am I going to connect being a curl with divergence being 0. And the connection, again, I mean, you can just, following the pattern on the page, Gauss's divergence theorem right there, saying that boundary fluxes are triple integral with divergence. That's the connection that shows that this sort of third blue equation and this bottom green equation are equivalent, and therefore that all these statements are equivalent, and therefore that I have my local test. And again, my local test is really easy. If you want to know, hey, is my vector field a curl? Is my vector field surface independent? Compute the divergence. See if you get 0. If you do, you're all good. And your vector field surface independent. So, really nice little argument. Again, really worth taking a little bit of time to digest not only how does this argument work, but how is this argument morally the same as this argument, which is morally the same as this argument. They're shameless rip-offs of each other. Okay. Let's do an example. This is a tricky example. It's geometrically... Oh, there's a little geometric landmine on here. And before we get into the question itself and how to solve it, I want to talk about the geometric landmine. This is really easy to mess up. So many students mess this up. And again, if you make this mistake, you're going to be off in another direction that has nothing to do with the question that's been asked. It's so dangerous. It's dangerous because that means that nothing you will subsequently write down will have any bearing on the question at hand. It's all kind of garbage. So very, very dangerous. Now let me show you what the landmine is. The landmine is in making sense out of what this surface is. So what exactly is that surface? Okay, let's do it. That's a elliptical paraboloid, flashbacks to chapter 2. I hope everybody's good with that business. There's a stretching out of a rotation. You remember all that stuff from long ago. And this is this elliptical paraboloid like that. Now, it says here we're looking at the part where z is positive. So in other words, the part above that blue plane. And thinking about that purple surface and the blue plane, here's the landmine. Here's what a lot of students do. A lot of students will then draw this, followed by that, and then, fooled by their own picture, mistakenly believe that this surface S is kind of a round, kind of an upside down bowl that has a flat bottom to it, and that this is a closed surface. Because that's what the picture kind of looks like, doesn't it? It's not. This surface is not a closed surface. This is an upside down bowl. End of sentence. There is nothing. There is no flat bottom on this surface. This is an upside down bowl, and the cereal just falls right out of the bowl. All right. So now let me make sure we're clear on why this is the case. So again, I claim that this is a misleading picture. Our surface is really just that part. And it says so right in the statement of the question. S is part of that elliptical paraboloid. S is part of the elliptical paraboloid. This business about Z over here, that's just a clarification of which part we're talking about, right? But S is part of the paraboloid, and if you look at this gray thing that I have down here, these points in this gray region, they're not part of the paraboloid. Does that make sense to everybody? So, like I say, this dangerous little landmine territory, please be very, very careful, right? When you see questions like this, a huge source of catastrophe on these kinds of questions is to kind of just a little too fast and loose with interpreting the surface and draw a quick picture and then pick the wrong surface. And then again, you're off in left field. You'll be applying completely different methods that have nothing to do with the question at hand, and it's a real problem. And it's, from a scoring point of view, it's not good. Okay. All right, how are we doing? Does everybody see why this is an open surface, not a closed surface? Feel free to talk to me after class, or feel free to come to office hours or whatever if you're a little weirded out by this, if you're not sure why, or if you're not sure you're buying this assertion here, or how you would figure this out in a different context. Make sure to come talk to me. We want to make sure that we get that 100% straight. Okay, all right, so that noted. Let's see here. The question is to compute a flux. And there's different ways to compute fluxes. We're going to be using our brand new tool here. Our brand new tool says, hey, take the divergence, see if you get 0. If you do, surface independence is on the table. And surface independence is fantastic. Surface independence says if you don't like the surface you're dealing with, all right, no problem. If you're surface independent, you are perfectly welcome to just pick a new surface and use that new surface instead. Is awesome. Pick your favorite new surface. Okay, so let's see how that would apply down here. Again, our existing first surface, the S is that part of that surface. That's this thing. Now, by the way, real quick, I'm going to ignore orientation in our first pass here, just so we can kind of get through and see the broad strokes and get to an answer. Let's get a one in the win column, and then I'm going to go. There's some little particulars with orientation we do have to worry about. But that surface, its boundary is that curve. We take the divergence per above. We get 0. We declare surface independence as a result. Right? And that means I'm allowed to pick any new surface I like. And I tell you what I like. I like this one down here. I like this, the shaded region down here in the XY plane. Has the exact same boundary. Right? Same curve. Same purple curve here for the boundary. So I don't need to deal with this green surface anymore. I can just deal with this much nicer, flat, z equals 0. Right? All sorts of good news about this blue surface. I'm going to use that blue surface instead. And surface independence gets the credit for allowing us to do this. So fooey on the green surface. I'm going to look at this blue surface. The blue surface is actually really easy to work with. The normal vector is vertical. I claim it's downward. We'll talk about that detail in a moment. But vertical, we'll come back to the other details. That means that when I dot with my vector field, right? You got that green vector field, dot my blue normal vector, easy dot product. That dot product is just minus xy. And now check it out. I have, at this point, a scalar surface integral. That's a scalar surface integral computed over that new surface. And scalar surface integrals come with the advantage that we're allowed to make symmetry arguments. And turns out, not only does this domain, this new domain that I picked, not only does that have a couple of nice symmetries, the integrand has the exact same nice symmetry. So pick your favorite symmetry up here. Show that your integrand has the equivalent odd symmetry, and integral 0 by symmetry, and we're done. And we didn't have to parameterize anything, right? Imagine what we would have had to do. We'd have to parameterize this thing and go through and compute the capital N and the blah, blah, blah with it, plug the parameterization into this thing. It'd get out of hand. The domain would be an ellipse. I'd have to figure out how to do an integral on an ellipse. It could be bad. And look at what we had instead. The hardest thing, computation-wise, was I did have to compute a couple of partial derivatives to establish the divergence was 0. They were easy, super easy partial derivatives. This was awesome. Very powerful. Is everybody on board so far? Now that I think about it, I guess we are out of time. So we'll pick up and talk about orientations on this next time. Yeah, y'all have a good rest of your Wednesday. See you Friday. And don't forget about it.